Hello everyone, welcome to Core Dynamics. In this video, we are going to see how to simulate large eddy simulation using OpenFOAM. The case which I have taken is the Vortex shed tutorial from PimpleFoam. It's from the OpenFOAM ESA version 2406 tutorials repository. If you have not installed version 2406, I will drop down the link in the description, the installation tutorial video from my channel, so you can check it out. If you have already installed, you can follow this tutorial along. Okay, now the case which I'm going to take is in this location. If you go to OpenFOAM version 2406 tutorials, incompressible PimpleFoam LES Vortex shed. So under LES you have a lot of tutorials, but for this case I'm going to take the Vortex shed. I'm going to copy this entire thing and put it in a new folder. So I have created my folder in this directory because I have ample amount of space here, so you can do it anywhere that you like. Just make sure that once you create it, you are inside this directory, and then I'm going to open my WSL here. Okay, I'm opening my WSL. If you just open it through here and then navigate to this location, anything is fine. So this is just my preferred way. And the first thing which we are going to do is create a para.foam file so that we will get the ParaView file here. Okay, now let's start understanding the case. Let's open the readme file, and it's saying this is a summary. Okay, the vortex street generated from flow over sphere, but we are going to use the LES. We have already seen how to do this using RANs, but now we are going to use the LES case, which is the large eddy simulation. And also in this case we are going to calculate the acoustic pressure based on the curl sonology. So this is an existing function in OpenFOAM, so you don't have to write anything to calculate this. You just have to give in some input parameters and it will do the work for you. And for the case details, the cylinder diameter here is 0.04 meters, of course, because OpenFOAM is always in SI units. The flow speed is 0.025 meters per second, and if you want, you can calculate the Reynolds number. It will turn out to be around 100 for the diameter which we have chosen. The kinematic viscosity is taken 1e minus 5, and which is kind of air. For this Reynolds number, the Strawhall number is calculated to be approximately 0.159, and the shading frequency is around 0.1 Hertz. So that is also calculated based on the Strawhall number. If you want to know what is Strawhall number, I have made a video on how to calculate Strawhall number using ANSYS. I will give the link in the description. You can check it out. And based on that, if we do the fast Fourier transform, which is the FFT, you will be able to get the shading frequency. Okay, so you take the Strawhall number and it will be like a wave like thing. Okay, so you take the waves, and if you do the fast Fourier transform, you will be getting what is the peak at which the shading is happening, which will give you the frequency. And in this case they have calculated it. Okay, now we have seen what is there in the readme. Now let's start understanding the case. So if you go to the allrun file, you will be able to see this. Okay, and the first thing which they are doing is restore the zero directory, because if you see we have 0.original, so we will be copying this and putting it into a new folder called the 0. So that is the first step. And then we are seeing something new, which is like converting an M4 block mesh file into a normal block mesh dict file. So let's see what that is. If you go inside your system, you'll be having blockmesh.m4. Okay, this is already given by OpenFOAM. So if you open it, you will be able to see these things. Everything is a defined function here, and if you scroll down, you will be able to see these vertices normally, but it has these variables instead of direct numbers, unlike what we usually see. And even if you go to the blocks, you will be able to see only the variables instead of the direct numbers here. So if you go here, you will be able to see they are calculating it based on some input features, and it is calculating the values for you, and it will input here. So that is what the M4 file is. So this will come in handy when you want to change certain parameters and calculate everything depending on that. Okay, so here we have been given a surface.obj file. So let's try to visualize it. I'm opening my ParaView. Initially we won't have anything so we can delete it. I'll load my surface.obj, and you can see that we only have a surface, nothing else. You go to surface.edges, you will be able to just see a surface. You can't rotate it because it's just 2D. If you go to isometric, you can see that this is just a plain surface, and we don't have any cylinders as of now. So that is what this is doing. So this will take the surface and it will put a hole through it and give it to you as a block mesh. Okay, now let's see how that works, but let's finish off our all run. Then we are running the block mesh. Then if you want to run your case in parallel, then you will decompose it and then run it in parallel. That's it, nothing much complicated. Then maybe you just want to post-process this, okay, to create a surface of the noise detect points and surfaces, but that is optional. Let's just understand how to run the LES case. So the post-processing is a different video, we will see it in a different setup, but now let's start with the case setup. Okay, the first command was to restore the 0 directory. So that's what I'm going to do here. And with this command, we have restored our 0 directory. Now we have all our files here. You can see that there is a new T and new tilde file, that might make you understand that this is using Spalart Allmaras turbulence model. So let's check what is under turbulence models. And thankfully, yes, it's Spalart Allmaras DDES, which is detached eddy simulation. So that is what we are using here. That's the turbulence model, which is also a LES model, and we are keeping the turbulence on, the print coefficients on, and there is the Van Rest coefficients. So you can see what this is if you go to the OpenFOAM documentation. So if you go here, they have given what this actually means. So this is a damping function. It includes additional limiting and apply to the region up to y plus of 500. So since this is like an external aerodynamics case, we are going to use this, and they have given the model function. So you can take this and you will know what are the optional entries, what is a mandatory entry. So that is what we are able to see here, and you can explore this with the help of documentation. Okay, now what we have to understand is we are using LES, and the LES model is Spalart Allmaras DDES. Yeah, so it's delayed detached eddy simulation, and you can see the mathematics here, and this is the LES turbulence model. So all you have to define is this, and this model will be used. Okay, you can check what are the wall constraints and everything, but to run a case, this is enough. Okay, now let's go and see what is there in turbulence properties, sorry, transport properties. It's 1e minus 5. That's the new kinematic viscosity as it was mentioned in the readme file. Okay, so that's it about the constant parameters. Now let's see what is there in the boundary conditions. So I will open all of these here. Okay, if you take the velocity, you are able to see that there is inlet, there is outlet, there is front and back. Because it's a 2D case, it's mentioned as empty. The top and bottom is considered slip, and then we have our cylinder, which is again no slip. Okay, and the inlet is 0.025 meters per second in x direction, and the outlet is kept as inlet outlet with a value of 0, uniform 0. If you go to the pressure, you can see that the cylinder, the walls are 0 gradient because we already defined the velocity, and the outlet is fixed value and they are keeping it as 0. So we have to define this psi, p0 and gamma. The psi is defined as none, the rho is defined as none. So this is like the total pressure is defined. You see here it is in kinematic pressure, so you have to change it to total pressure, and that's why this setup is done. If you want to keep it as normal outlet condition with fixed value 0, you can still do that. So this is what is there in the case, so I'm going to follow it blindly. And the top and bottom is 0 gradient because it's a wall, front and back is empty, just like what we would expect. Now coming to nu t, which is the turbulence viscosity, they are using nu t u Spalding wall function. So since we are using Spalart Allmaras, this is the most appropriate one, and that's why we are using nu t u Spalding wall function. And for the inlet we are using calculated, and for outlet top and bottom it's again calculated. And the internal field is usually set to 0 or a very low number. In this case it's 1e minus 5, and the front and back is again empty. Now coming to the turbulence file, which is our new tilde, which corresponds to the Spalart Allmaras case. So if you want to understand new tilde, you can go so if you go here, you can see that new tilde is a modified turbulent viscosity, so which is like a ratio between the omega and the epsilon. So to understand it better, I will give a video link in the description of Fluid Mechanics 101 channel. So he has explained the new tilde very well, so you can check it out. Now coming back to our code, we are going to see the cylinder has 0 gradient, which means the solver calculates it for you, and the inlet is fixed value because we are already defining the velocity, so we also have to define the turbulence. And the internal field is taken as 1e minus 5, which will come here. Similarly for outlet, it's taken inlet outlet because that is also what is taken for the velocity, so we are following the same pattern here. And for top and bottom we already defined the velocity, so it is again 0 gradient, and the front and back will be obviously empty. That's it for the boundary conditions. And coming to the system, the first thing which we have to understand is what is in FV scheme and FV solutions. See, if you go to any FV scheme, that is what is going to define how your solver is made of. Okay, so in our case the DDT scheme is necessary and it is kept as backward, and if you want to check the documentation and understand it, you can do it. And the divergence scheme is taken as Gauss, and under Gauss there are many methods, so they are taking LUST, grad U. And for interpolation scheme it is taken as linear, the Laplacian is Gauss linear, and the wall distance is necessary because we are using Spalart Allmaras. If you don't put this, it will throw an error. So the wall distance is necessary for both K, omega SST as well as the Spalart Allmaras. Okay, now that's about the FV scheme. Coming to FV solutions, we will be able to see all these relaxation parameters, and you can see that it is using the pimple algorithm here to solve it. So that's why we have this pimple function with the n outer characters as 5, in character as 2, and there is no non-orthogonal characters in this case. And you can also check what are the relative tolerance and tolerances here. If you want to explore, you can try modifying them. Okay, now let's try to understand our control depth file. You can see that we are using the pimple foam because it's a transient solver, it's an incompressible solver, so we are using the pimple foam. And the start time is obviously 0, the end time is kept as 200 seconds. The delta t here, it's not kept as adaptive time stepping, so it's just constant delta t. You can see that it is 1e minus 2, which is like 0.001 or 0.01, sorry, 0.01, and the write interval is 100. For every 100 time steps it will write one case file, the time step file. So in our case it's the delta t is 0.01, and when we multiply by 100 we get the files for every 1 second of flow time. That's the calculation here. The purge write is kept as 50, which means it will keep only the latest 50 time steps. All the other files will be removed so that you will be able to save the space on your hard disk or okay. The write format is binary. This usually conserves more space, it will not use a lot. The other option is ASCII. If you want to open and see any of the files, then you can keep it in ASCII. You can't open a binary file in your VS Code or any text editor. Okay, and the runtime modifier is kept to true because sometimes we might want to change the end time or delta t, then we can do it when the simulation is running. You don't have to stop it. Now coming back to the functions, these are the user-defined functions for post-processing. And we have the turbulence fields, so this will write two fields, one is the FD and the other is the LES region. So it will write two turbulence fields which we can actually visualize in our ParaView. Then we have our minimum maximum function, so this will write two minimum and maximum. So the one line will be the minimum and maximum of velocity, the next line will be minimum and maximum of the pressure. So this will be a post-processing text document file. Coming to the curl surface, so if you want to understand curl surface, you can check the documentation. So this is a function based on the acoustic pressure based on curls analogy, and this is the formulation, and we have many parameters here. If you check, these are mandatory entries, so that is mentioned here as well. If you go here, these are mandatory entries: the type, libs, input, output, patches, C0. And what is C0? This is the speed of sound, the reference speed of sound. It's a scalar value, so you don't want to change this. That's why it's mandatory entry and it's unmodifiable. You don't change it. Then coming to the observer's position, these are the points from which you are trying to evaluate the curls analogy, and you can define these points in 3D coordinates, and here it's actually done. Right, so you can see there are 4 points based on north, east, south and west. There are 4 points and it will be calculated there, and this is for curl point. Similarly, we have the curl surface on which the end site format will be written, and this has to be post processed. So that's for another video, otherwise this video will get too lengthy. The curl point is calculated on these reference points, the observed positions. Then coming to the cutting plane, the time start is at 100. Actually, we are not going to let the simulation run till 100 and all. So you just understand what this is. There will be a surface file written based on the n-site format, and the cutting plane, this is the point, and through this point, through this plane, there will be a plane created and it will write all the values on it. So it is a cell point interpolation, that's what we are trying to take, and the usual forces. So this will give you the CDCL values. The center of rotation is given here, and the patches is on the cylinder. The time start is 100, and we have given the rho infinite as 1. This doesn't matter because we are using incompressible case. Okay, so that's all about the functions as well. I think I have shown you everything, and this is just the post-processing files, the noise depth surface and noise depth point. If you want, you can remove it because we are not going to do the post-processing here, but let's just proceed and run. Okay, after we copy this, now we have to do the M4. So the M4 is going to change the block mesh depth into normal block mesh depth. Okay, instead of .m4 we are going to write it out. So this is the syntax: write out into this file. The function is m4, so we are writing it out there. And if you check now, you will have the block mesh depth. You can also check from here. So not just the block mesh depth.m4, you also have the block mesh depth, and that is what we wanted. Now we can run our block mesh. Okay, now we run our block mesh. You go to ParaView. We don't want 2, we just want 1. Now you can see that there is a cylinder and there is the mesh around it. So we got this O-grid. Okay, so this is a very easy way. Now if you want to change the diameter of the circle, all you have to do is just go and change the block mesh depth, and you can use the same mesh for any other case. Like if you want to perform vortex shading with runs, you can use the same mesh actually. Okay, now we have the mesh, and if you see in the mesh we have empty phases, patches. So the front and back will be empty, as you can see here. This is just the front and back. We have 2 surfaces and those are empty. And coming to walls, the cylinder is kept as wall. The top, bottom and all are not actually walls, so those are slip, so we are not going to consider it as wall. So let's view it, top and bottom. Right, we have top and bottom, and there is inlet and outlet. We have this as inlet, this as outlet, and since it's 2D, we will have only 1 cell thickness. Okay, now let's go back to internal mesh. Click on apply, and let's just view the surface. Now if you don't want to see this depth, you can press this 2D here, the 4th icon, and it will become 2D. You won't anymore see the thickness and all. You just go to the Z plane and you can just see the 2D, and you can move now with your left click instead of the middle mouse. So that's a slight change that will happen in ParaView. Okay, now let's start looking at our decompose product. So now we are going to run the case in parallel, and I have made a slight modification. Like I'll be using the Scotch method instead of simple. By default, it will have simple. I have changed it to Scotch, and the number of subdomains for my PC it is 8. So if you want to know how to know for yours, open your task manager. Go to this second tab on the left, which will be the performance, and click on CPU. Now here you can see what is the number of cores. There will be number of logical processes as well, but just check what is the number of cores. In my PC it's 8, so you can choose the number whatever is yours, and you can enter here. Make sure to save the file. Go to the terminal and type decompose path. Okay, now the case is decomposed. We have a zero and constant inside every processor file. Now we can run the case in parallel. I'm going to run MPI run NP8. So if you had entered any other number like 4 or 6 in your decompose product, then you might want to enter the number here, not 8. Then type PimpleFoam because that is our solver, and then parallel. So these are like mandatory keywords. You have to do this, you have to do that, and this is your solver's name. Okay, then you just have to press enter and make sure the simulation is running without any errors, and wait for the simulation till it reaches some time step. So let me wait till it reaches 5 seconds of flow time, so you can check it here. Right now it's 0.16 seconds. So once it reaches like 5 seconds, I'll be back. Meanwhile, you can check inside the post processing folder. It will be automatically created. Inside that you'll have the curl point, and you'll have 4 observer data, and it will also have the min and max, which will have this file, the data file. Like as you can see, one line is magnitude of u. You will have the minimum, the location of minimum, and which processor it occurred at, the maximum point, the location of the maximum, and which processor it occurred at. Okay, so for our case, min and max both occurred at the second processor, and the second line will be of pressure similarly. So it's like alternate. You can see that 0.1 and 0.1 is the time seconds, and it is appearing twice, one for the velocity, one for the pressure. So you can use C or Python to post process this. You can extract the data, the u into separate file, p into separate file, and based on the time you can plot the graph. So this will be writing for every 0.01 seconds. For every delta t, this will keep on writing. You can refresh to see more and more data, and this is for minimum and maximum. Similarly, after it reaches 100 seconds, it will start writing our forces data as well, because we will be using the forces data to actually calculate the straw hall number and everything. We'll be using the pressure, and we can take the CL as well. So let's just wait for this simulation to reach maybe 5 or 6 seconds, and I'll get back to you.
A few moments later.
Okay, the simulation reached 5 seconds, so I stopped it, and now we can start visualizing. So to do that, you can go to your ParaView, and I did not reconstruct the case. So from here, you can change it to decompose case, click on apply, and if you click here, you'll be able to see the velocity, be able to see the new tilde, the new t, the pressure, and additionally you will have the turbulence properties because we wrote the functions out. So this is the LES region, and this is the FD. Okay, and we have the velocity. So if you hit play, you can see how the velocity is growing. Similarly, this LES region will keep changing depending on the flow, and we also have the pressure. So we have this. Once the vortex shading starts, you will be able to see the shading here. So if you let it long enough, you will also get the CL data, which will allow you to calculate the straw hall number directly. So it's up to you. It's up to the post processing. Maybe I'll try to make a video on how to make the fast Fourier transform for OpenFOAM. And that's it for this video. If you have any specific questions about this video, you can ask in the comment section. If you enjoyed the video so far, consider dropping a like, consider subscribing to the channel. And if you have any video recommendations, please drop it in the comment section. I will try to make it. Thank you. See you in another video.